I could, but I am so locked into the I'm so locked into my ecosystem. It would cost me a lot to switch to Android. No, and I'm not a fanboy, so I would switch if I thought there was good products there, but I'd have to switch everything. And not just me, the whole house, all the stuff, all the streaming services, yeah, I'm not doing it. All right, I'm waiting for the word to show up there so we can get going. Energy for orbits is a little weird. So let me just start off by saying we have gravitational potential energy. Not wrong. I don't want to use that statement because the definition of potential energy is still the same. We've been dealing with potential energy in a very focused manner. For what we've been doing, potential energy has been about relative comparisons. So although everything we've talked about when it comes to potential energy has always been something like this, MGH. If you go all the way back to when I first introduced it, so we're talking way back in like October and November, I always wrote it as mgh minus h naught as a reminder that gravitational potential energy was always measured relative to some other point. And this is because, and this part's very important, the actual definition of potential energy is minus the work done I don't want to say against. The work done by a force. That's how it's been defined. And it came out negative, if you'll recall, because if you have an object and you're moving it from here to here, the work done by gravity is negative. Because gravity is pulling downwards, but the object is moving to a position that is upwards. One more thing to remember here. Work is force times distance times the cosine of the angle. So if your distance was upward, but the force is downwards, then gravity did negative work. This is just the way it's defined. So when you do the calculation for work here, you would have gotten negative mgh minus h naught. That's how much work is done. And gravitational potential energy is minus the work done. So that means it turned out to be positive. I'm just throwing at you all the little stuff we did way back then. And I told you not to worry about it because it's no big deal. Energy is energy. Stuff has energy. Okay, for this, you got to throw all that away. We treat potential energy when it comes to gravity outside of the Earth different. And the reason is not as complicated as you think, but the answer is going to look complicated. The reason is because when you're talking about 2 points on the Earth, all the things that you're comparing are on the Earth. So if it's a roller coaster and you want to talk about how much potential energy you have at the top of the first hill, well, we're comparing that to the ground, and everybody who is making this observation is able to stand on the ground and observe this event. We can't do that if we're talking about going from the Earth to the moon or from the Earth to Mars. There's not the same point of comparison when it comes to energy. Now, before I go too deep into this and you start giving me that look like, why are we bothering? Well, you're right. Not all of you are going to be rocket scientists. But here's why I'm bothering to say this. If you're actually trying to do this, if you're the person who's tasked with figuring out how to go from here to there, you need a relative point of comparison between the two places so you can figure out how much fuel it's going to take to get there. Energy requires fuel. You're determining that. So the reason why we do it the way I'm about to describe is because it allows people who are in that field to make relative comparisons now between one planet and another, instead of where we just have it on the surface of the Earth. So using the surface of the Earth as your comparison or any kind of relative measure that's in the same room will not work for gravitational potential energy. So the way gravitational potential energy is defined when dealing with orbits and planets is different. And it's on your equation sheet already, but I want to explain where it comes from and why. What we say is that the zero, the place where there is no energy, is a place far enough away where the two objects are not experiencing any force of attraction due to gravity. I know that's a whole big sentence, so I'll say it again. We say the point that is zero, the point where two objects have zero potential energy, is when they're far enough apart so that they experience no force of gravity. So here's our expression for force of gravity. The only way F can be zero is if R goes to infinity. So we say that there is no energy when two objects are infinitely far away. Now, what that's going to mean for us is that when we describe gravitational potential energy, we are describing it as a point that you really can't get to. But we do that as a means of having a place of relative comparison. On the AP exam, they will say it just like that. Calculate the amount of energy in the orbit compared with a point infinitely far away. They're not going to ask you why you have to compare it, but they're going to make that statement. And when they make that statement, they are telling you to use a specific method of calculating energy. Now, I don't want to spend a lot of time on this portion where this comes from, but this is how it's calculated. It looks very similar to the expression for the force of gravity. You'll notice there's just one less R there. And for those of you who are a little bit mathy, I've never seen them ask us to do this, but it comes right from this. Potential energy is minus the work done, and work is defined by an integral. We've dealt with work most of the time where the force is a constant, but this is a situation in which the force isn't constant. So if you do this math, and all of you in calculus should be able to do this. So you say, calculate the work done moving a particle from infinitely far away to a point that is close. You get the function I just described. That's the math of it. I don't care if you know anything about how the integral produces that. You won't ever need to worry about that. But what I'm about to say next, these are the things you need. We state that objects that are attracted to each other by gravity exist in what's called a potential energy well. It's kind of like this. Imagine the ground is up here. There. Imagine the ground is up here, and you dig a very deep hole. But you state that the ground is h equals 0. So if you drop a rock down the hole, the rock's going to be at the bottom of the hole. It will take energy for the rock to get out of the hole. You could jump down there and join the rock, and you could give the rock kinetic energy, and if you give it enough, it'll get out of the hole. We treat gravity the same way. We say that this hole represents a negative height, and objects are trapped in that hole. So things that are on the earth are trapped here. They can't leave. If you give them enough kinetic energy, they might. But you have to give them a lot of kinetic energy to leave the earth. So we treat this as if the energy you have is negative. And to that end, all stellar objects, all celestial objects, therefore, have the same relative point of comparison, a point that is infinitely far away. And that way, all of these energies that we calculate are made to be comparable. So you can compare the amount of energy you have in orbit around the Earth with the amount of energy you have with the orbit around Mars, and because they're based on comparing it against the same place, they're a comparable amount of energy. And therefore you can use our rules on the Earth to calculate things like how much energy you would need to go from one place to the other, how much fuel that would require, what you would have to do to your spaceship to do so. That's why we picked this relative point of comparison. But what it means is that any object that is near a planet or a star will have a negative amount of energy. And that includes if it's in orbit. We still will calculate things the same way. We still say that there are conservation rules. And conservation will still be the sum of the gravitational potential energy and the kinetic energy for objects that are in orbit. But this number will always be negative. If you're in orbit, you're still trapped around the object. So this number will always be a negative number. It will only become a positive number if you have escaped the object. And that's the only time the energy for a rocket would ever be positive is if it had enough energy to escape the Earth. Now, I want to be very clear. Escaping the Earth means leaving the Earth entirely and not falling back into it. So that's different than just going into orbit. Orbit is a lot less energy than the energy required to escape the Earth. So let me give you the first application. Application number 1, what's known as escape velocity. Our rockets never achieve escape velocity. We never give them enough energy to leave the Earth. And just to be square, leaving the Earth means going infinitely far away. In the history of humanity, only 2 objects are even close to that have been launched by humans. Voyager 1 and 2. Everything else, not so much. Now, we have other objects that are getting pretty far away now, too, and they nearly had escape velocity. But I say nearly. Everything else you've ever seen on the news or any video of a rocket launch you've seen never achieved escape velocity. Even to go to Mars, you don't achieve escape velocity. Because although you might be able to escape the Earth, you're not escaping the sun. Everybody understand that? There's something bigger always around. So escape velocity is still relative. But when you're asked to calculate escape velocity, you're asked to figure out what it would take to bring your potential energy to 0. When you're asked to calculate escape velocity, you're being asked what it would take to bring your potential energy to 0. That's achieving escape velocity. So what we say is, if you add enough kinetic energy to an object, it might get to a point where you have 0 energy. This would be the minimum amount of energy necessary to escape your celestial object. So the escape velocity is the result of that. Meaning if I want to figure out what the escape velocity is for a planet, well, then I have to know, first, the mass of you, the mass of your planet, g, and where are you relative to the planet? Are you on its surface? R is the separation distance. So we're talking about kicking one of us off the planet because we've had enough and we want to give them enough escape velocity so they can't come back. Well, then we are talking about a starting distance away being r, the radius of the planet. And we're going to add enough kinetic energy to make that happen. So we're talking about adding it to, we're kicking you off. And we're going to call this the escape velocity. This sum has to equal 0. That's how you escape a planet, or you escape a star, or you escape an asteroid. Again, we don't achieve escape velocity. We've never sent anything that far away. So the only 2 things that are pretty close, like I said, they're still not actually that far away, but they're not going to fall back. They have enough. So this is the first application. And again, it's called escape velocity. And it's a way to to visualize this idea of what it would take to get off the planet or get off the star or get off whatever. Be aware that the escape velocity could be solved here, and you understand that it will work out to be a positive number because you're going to move the potential energy over. So you're going to get this 1/2 my v squared equals my mpg over r. So you can cancel out the mass of the object. This is for calculating the escape velocity, not the energy. You can get rid of the mass if you don't need to worry about the energy. Multiply by both sides by 2, and you get your 2 mass of energy over r. So technically, this is the escape velocity. But in any case, you're going to be asked about it, you'll probably have to do all of that in order to earn all the credit. Okay? Most objects that we throw into space don't have escape velocity. Most objects that we heave into space are in orbit. So when we talk about circular orbits and energy, they're pretty easy to kind of discuss because they end up working out to be pretty simple math problems. So consider this situation, and I want to set it up for you because I think it's something that's in the homework or similar to the homework. Let's say we have a planet mass m, and we are located in a stable orbit a distance 3r away, where r is the radius of the planet. This is a pretty typical style problem where they'll give you distances that are relative to the radius of something. Be patient, because they could say that your spacecraft has an altitude of 2r. If you hear the word altitude, and I didn't cover this yesterday because I knew I threw a lot at you yesterday. Altitude is a distance above the surface. So if they say the altitude is 2r and they say the radius of the planet is r, well, then you are a distance 3r away from the center of the planet. So in this drawing, this refers to the altitude, but this is the separation distance. And I spelled separation wrong again, right? It's an A. Somebody corrected me yesterday. I don't know if it was in this class or not, but I'm pretty sure it's an A. So, oh, there, I fixed it. I know it's subtle, but look for those little things. You can see how they would trip you up on that. So just kind of be aware. Right now, with what's sitting here, you should be able to figure out what the speed of the spacecraft is based on what we talked about yesterday. Can you just get a quick expression for the speed of the spacecraft? Let's say the spacecraft is here, and again, it doesn't matter what it is. It's a satellite or something. Can you just figure out for me what the speed of the spacecraft is when it's in this orbit in terms of r, m, and mass of the satellite? We'll do ms for the mass of the satellite. This is just proving to me that you kind of paid attention and you have a little flesh in the game, and I can take a little break. We done with this one? Pretty straightforward, right? I hope. M satellite G over 3r squared. That is the unbalanced force between the two objects. Equals, it's the mass of the satellite that's in orbit times v squared over 3r. Because, again, 3r would be the radius in this case. So this gives us an expression for the velocity of the satellite. So cancel out those two. I get my mg over 3r under the radical equals the velocity of the satellite. Good? So I'd like us to calculate the energy in this orbit. The energy in the orbit is the sum of the potential energy that the spacecraft has and the kinetic energy that the spacecraft has. So the energy in this orbit is pretty straightforward to calculate. We know it has kinetic energy. It's the only way it stays in a stable orbit is to have a velocity that keeps it from crashing into the planet. So the energy in the orbit total will be U plus K. And in this case, that's negative M1, M2, G over R plus 1/2 mv squared. This will be how we calculate the potential energy plus the kinetic energy. I'm showing this to you because once you see it, you'll understand why they ask these kinds of problems. So, starting from here, there's my gravitational potential energy. That explicit negative sign is important. This is the mass of the satellite. But then plug in what we know for the velocity. The velocity is known because it's in a circular orbit, so it has to be a value that's related to the other variables that are here. So mg over 3r. It was under the radical, but we square the velocity so the radical goes away. It should be obvious and clear to you that these two things can be summed now. So negative ms g over 3r plus 1/2 ms g over 3r. When asked to calculate something about an orbit, you'll get terms like this that will sum together for circular orbits. By the way, common denominators, and then just add. And I think all of us know this is going to be msg over 6r will be the total energy. It's still negative. This term is still bigger than this term. Okay, what you've done is probably the most common example of an energy question dealing with an orbit. Calculate an expression for the velocity and then use that with your expression for the potential energy. Please notice the energy is still negative. You're still trapped around the planet. Being in orbit does not get you off the planet. It just gets you trapped a little further away. Does everybody understand? So you're still there. Does this make sense? Usually this stuff is pretty easy. It's just understanding when to use stuff for circular orbit and when not to. All right. If you have your worksheet, this might be good for you. We're going to talk about elliptical orbits. It's always circular orbits. Always. And even that, there's only about 6 of them in the last 30 years. So this is it. But I'm going to stick with the idea of using a planet here, but in any discussion when we talk about this, remember planet could be replaced with the word sun or asteroid or something else. So I'm going to stick with planet for now. I want to consider, and I've kind of tried to draw this for you guys, but it's best for you guys to try and kind of reason this out. Imagine you have a situation in which you are in a circular orbit. So I have some satellite here, and it is in a circular orbit, which means it has a certain velocity, horizontal velocity that is. Like this. Okay. Now we know that there is a specific velocity that is necessary for you to be in a circular orbit. If you're going too fast, you're going to screw that up. If you're going too slow, you're going to screw that up. So there's a special amount that keeps you in a circle. But because this isn't like you're driving on the road and you're going too fast or going too slow, if you reduce the velocity, and let's talk about reducing the velocity. So we're going to have a sudden change. That usually means that something pushed on the rocket this way and slowed it down for a brief moment. They fired the engines or something like that, or something struck it, which happens. Then suddenly the velocity is not going to be enough to travel in the circle, so the object will fall underneath the orbit that they had. It'll be a smaller orbit, but that orbit is suddenly going to become elliptical. In the case of this problem, this elliptical orbit will still come back to this point, right? This is the point at which suddenly its velocity is reduced, but it's now going to travel in a path that will take it closer to the planet, but then it'll come back out and be closer to the, or back to where it started from. This elliptical orbit begins and ends in the same place, the place where it had a sudden reduction in its velocity. But now it's going to fall towards the planet. And because it's falling towards the planet, it accelerates. So when it gets down to the other side of the planet, here, its velocity has increased substantially because it's falling. It's being accelerated towards the planet, and suddenly it's got a velocity here. And this velocity is too big to be in the circular orbit that's at this point. So let's just make the circular orbit that's here. So there's the circular orbit that's there. It's going too fast for that circular orbit, so it falls outside of that orbit. But on the way back out, away from the planet, it slows down again until it reaches this point here, where its velocity is too small to stay in the orbit where it is. Now, first, just because you should know things, this is how you change orbits. If you want to go to a lower orbit, you slow your spacecraft down, and then when you get down there, you adjust the velocity to be in your lower orbit. This object is continually passing between two different circular orbits because it's in an elliptical orbit. All right, a couple things that you need to know about elliptical orbits. There's not many, but just a couple things. First, in an elliptical orbit, whatever is being orbited is at one of the focuses of the ellipse. Did I say those words right? Yes. When you're in an elliptical orbit, whatever you're orbiting is at one of the focuses of the ellipse. Foci of the ellipse. Octopi, foci. Focuses. So it is super common, and I gave you a homework assignment that has it on there where you will be asked to draw what an orbit would look like. If it's an elliptical orbit, make one of the objects at the focus. Don't put it at the center. But people put it at the center all the time. It looks silly. You'll get it wrong. So whatever you're orbiting has to be at the focus. We call this point that's far away the apogee of the orbit. The part that's closest, the perigee. Those are the only two vocabulary words associated with orbits that you might need to know. Apogee, furthest away. Perigee, closest. You guys, we don't have mathematics that deals with the ellipses the way that will work here. So we don't have to worry about making calculations about, well, what does this look like? We don't have to do that. If they're going to give us an elliptical orbit, then suddenly you're free and clear. You don't have to figure out period. You don't have to figure out what the velocity is because of the size of the planet or anything like that. However, there is something about orbits that are true for all orbits, whether we're talking about circular orbits or elliptical. And this is what they'll be getting at. All orbits conserve energy and conserve angular momentum. There's going to be a question on the test, and they're going to use elliptical orbits. This is what they're going to ask. All of them conserve energy, and they all conserve angular momentum. The problem is that the only way for us to deal with a problem like this is for them to give us something about the orbit. There is nothing you can do to calculate anything about the size. So let me get some of this stuff that's distracting out of here and just talk about, let me just do this. They say, what would an elliptical orbit look like if the thing here suddenly got faster or the thing here suddenly got slower? They've asked that question a bunch. That's on the AP1 exam, and it can be on yours. But when it comes to calculations, picture of this already, I'm going to try and make something that looks more like your picture. You have one where the sun's off to one side like that. Is that right? And I've highlighted like this position, this position, this position, and this position. Is that right? All right. Energy is conserved. So if the object is going around the orbit this way, it's going slowest here and fastest here. Okay? But it's closer to the planet here. So the potential energy here is more negative than it is here. Right? The negative number is bigger because it's closer to the planet. R has gotten smaller. So the kinetic energy increases, but the potential energy becomes a more negative number. But the sum of the kinetic plus the potential has to be the same everywhere in the orbit. Because of that, this is one way to figure out the velocity at different points in the orbit, because the kinetic energy and the potential energy have to sum to be the same amount. Now, listen closely. That means that if they give you this distance, because all you need is r, and they give you the velocity here, you still can't figure out the velocity here unless they tell you how far away it is. Because the gravitational potential energy requires you know the distances. They have to give you all sorts of distances and all the things. But they could also pick this one too. And it's just fine. Doesn't make a difference which one they pick. They have to tell you what the distances are in order for you to figure this out. Now here's the thing I want you to write down in your notes. It is true, the potential energy and kinetic energy stay the same everywhere. And using energy will help you figure out the velocities in any of those places. Or if they give you the velocities, you could figure out, R for different places. However, and I want you to be really, really careful about this, momentum is also conserved. And because momentum is also conserved, it's easier to use momentum every time. If given a choice, use angular momentum, because it's a point particle. The angular momentum will be r times mv times sine of the angle. There's a problem with using this. It's got its own drawbacks, but it's just one thing. There's just one kind of angular momentum. So this has to be the same here, and it has to be the same there. I don't have to add two things together. I can add something smaller. And this is going to be a positive number. It's never going to be a negative number. So when it comes to figuring out a problem that has elliptical orbits, angular momentum is easier to use, except it really only works here and here. In any other place, you'd have to figure out what the angle is. And they never give you that. Okay? They never give you that. So although you can use either one of these in either circumstance, this one is the fastest for figuring it out, but only works at the apogee and the perigee. This one is longer to do, but doesn't care about any angles. Now, when I go back through the literature of all of the problems that have ever been asked, I can only find 2 FRQs that have a calculation related to an elliptical orbit. In 50 years, they've asked about elliptical orbits where you've had to calculate something about it twice. Draw it? Yes. They've done that about a dozen times. Drawing pictures. This is very unlikely. It's very unlikely on the test. Now, I don't want to see a whole FRQ devoted to it now, but it's very unlikely on the test. So, I know we're at the close of class, or we have only a few minutes left. I want to just pick up real quick and hit all the points here. First, elliptical orbits. All I really wanted to stress, energy and angular momentum are conserved, not linear momentum, angular. And in this case, angular momentum is always the point mass angular momentum. I want to go through the homework with you tomorrow. Please have done some before tomorrow. We're talking about, say, So you're the white dot there. That's the Earth and that's the sun. There is an escape velocity to leave the Earth. But if you were talking about the escape velocity for the sun, well then this might be the R for the sun, while this is the R for you and the Earth. There's more than one escape velocity then, or at least there might be more kinetic energy you have to add if you're trying to escape from the sun. So under something like this, there'd be the potential energy from the Earth because you're close to the Earth, plus there's the potential energy from the sun because you're also stuck around the sun. And we can add these together because they were both made relative to a point infinitely far away. That's why we could do that. Now, to be perfectly honest, away from you guys just passing exams, it's a bit of a ridiculous calculation. Do you guys understand that? So the idea of being asked to calculate the escape velocity, they'll be specific. And I've only seen it on one multiple choice test for years. So it doesn't come up often. But again, it's been on the FRQs. They ask it not infrequently. And so they will talk about the escape velocity. They're generally only ever talking about the planet at hand. So they might say, what's the escape velocity for? And they'll give you something. They'll say something about a planet, or they'll make up a planet. They're expecting you to take the potential energy, add to kinetic energy, and set it equal to 0. They're expecting that. And they're likely to give you a point for making that reference. Ultimately,